Okay, so we are going to start with some new notes, but before I do that, I wanted to talk just about the change in class that I had mentioned in one of the Zoom meetings. And so, what we're going to be doing for this next chapter, we're going to kind of trial it. If you guys like it, we'll keep doing it. If you hate it, just say, let me know, hey, Mr. Ewert, this, video thing isn't really working out. We really liked the way we did it with the first chapter, the limits better, and we'll go back. But I'm really excited to try this because really what it's going to let us do is we're going to end up starting to do the homeworks during class time. And we'll have myself, we'll have a Gear Up tutor, and we'll have Kyra, who can all help you guys and give you guys feedback. So each day you might have a different one of us helping you. But you guys will be able to get a lot more feedback and a lot more help. And we should be able to finish the homeworks really during class. So you won't have too much homework, if any at all, outside of watching a video. So, just about reading this calendar, anything that's underlined is the previous night's homework as a video. So, the reason I did that is just, basically this page 72 to 77 are the notes. They kind of match up with day 12 homework. But this would be the homework that would be due on the 7th by midnight. Right? Page 80 to 83 would be the homework that would be due on the 8th. So it's, you watch the video, we've done this before, you take a picture of your notes and submit that as a PDF, free 500 points. Then the day, say like the day 13 homework would be due by 3:30 p.m. on the day of the 9th. Now, technically, honestly, I'm going to give you full credit if you turn in by midnight. But if you guys saw like the new attendance thing, basically if you turn it in by 3:30, I'll give you a 4. When I'm doing your attendance. And if you turn it in by 11:59, I'll give you a 3. Honestly, I don't really care. It does not matter if you get a 3 or 4 for attendance. They don't contact your parents unless you're getting a bunch of 1s or 2s. And that would be like you're just not attending the Zooms. So it really doesn't matter if you turn those in by 11:59 or 3:30. But hopefully most of the time we can finish them in class, and so you can turn them in right then, which is great. So with that, we're going to go ahead to our next chapter of notes, and that's the chapter 2, which is like the derivatives chapter. So our first, if you don't have this unit 2 packet out, pause this video, go get it, and then start the video up again. So we're on page 72 of the unit 2 packet, which is our first page. So our first lesson is going to be on something called the difference quotient. And so we're going to start this new chapter, and it's all about the derivative. Okay, calculus is mostly 2 big concepts. It's derivatives and integrals. So like the next 3 or 4 chapters are all going to be about derivatives. So we're going to kind of start looking at what is a derivative. And before we do that, we're going to draw a picture. I'm just going to kind of draw a parabola. It doesn't quite matter what your parabola looks like, but just kind of an upside down parabola. And I'm going to go ahead and just kind of pick a value over here. We're going to call this value x. And we'll pick a value over here. We'll call this value x plus h. Okay. And so what happens is that this difference between them, from x, the distance from x to x plus h, the distance would be a distance of h, right? That would be the difference. Like if this value is 3, this would be 3 plus 7. If this was value, that's my fault, I jumped ahead of myself. If that value is 3 and this value is 10, it would be the same as 3 plus 7. So the h would have been 7, right? That would have been our difference, okay? Now, I'm not going to use numbers. We're just going to call them x and h. So we're going to plot a couple points in here. So we'll put a point at x and a point at x plus h. And so if we did these, the y value, we don't know what it is, so we'll just call it f of x, right? You'd plug in x to the y value. Here, we would call the x value x plus h, so our y value, we would have to plug in x plus h. So we're going to start with that, okay? And I want to look down here. What does the expression f of x plus h minus f of x all over x plus h minus x, what does that represent? What does it look like to you? Kind of think in your head, what does that look like? And if you were thinking, okay, f of x plus h is the y value minus another y value over the x value, x plus h minus another x value, that's kind of looking like, our equation for slope, y2 minus y1 over x2 minus x1. That's actually exactly what it is. So that's the slope formula. Now, it would need to be for a line, right? So if we kind of connected these two, wish I had a ruler on here. So if we connected these two, we call this line, any line that connects 2 points on a curve, we call a secant line. You might have seen that in Math 3. If not, you're seeing it now. So a secant line connects two points on a curve. So what this is going to be, this formula, it's the slope of the secant line. So it's the slope of that black line that I drew, that secant line. Now, can we simplify it? Yes. So f of x plus h, you cannot distribute this. It's like you're plugging in x plus h into the function. So nothing cancels out, but x plus h minus x, the x's cancel out. So that's our simplified slope. So this formula here, that is the slope of the secant line. Okay. Now, what if we decided to decrease that value of h? Right, so if we kind of took this point and we started moving it to the left along the line. You know, we put it here, we put it here, we started making h smaller and smaller. So instead of doing it here, I'm going to do it in Desmos because it just looks fancier. So I kind of have a parabola just like how we had, and we'd make h bigger. This is about what we had ours looking like, you know, something like this. And so we can just start decreasing h. And as we decrease h, we see that the slope is changing, right? That slope of that line is changing. And so the question I had for us is, what if we, you know, as h changes, what if we kind of make that distance, that h, approach 0? So what if we started to make that h smaller and smaller and smaller? So here's 1.8, right? 1.2, 0.7, 0.3. I'm going to even, you know, make it say 0.2, 0.1, and let's just kind of have it at 0.1 right now. So what do you guys see, you know, kind of think in your head? I know we're on a video, but think in your head, you know, what does this line look like compared to that point? You know, this point Q is our point at X. And if we really zoom in here, we did this before, with the sine x over x, that limit. If I zoom in, you know, a lot, what we see is these two lines are not the same. You can see kind of the red line and the black line are, you know, coming apart on the edges. But if we really just look right in around that point, they're overlapping. They almost look like the same line. And so that's approaching something that we call the tangent line. Okay, a tangent line, again, you might have seen this hopefully in Math 3, but if you didn't, or if you took engineering with me, we may have seen this at some point. But a tangent line is a line that touches a curve just in that one spot. Okay, so a tangent line touches a curve just in one spot. And so as that distance gets smaller and smaller, the secant line essentially approaches the same value as what a tangent line would be. So as h goes to 0, the secant line, we'll say the secant line becomes the tangent line, or it kind of approaches the tangent line. And again, if you need to, in your notes, kind of add that in, you know, a tangent line touches a curve in one spot. So our secant line, right, our secant line, it had 2x values, right? 2x values, right? And it's connecting the curve in those two spots, whereas a tangent line is only touching it in one spot. Okay. So what that kind of means is that if we made h approach 0, then what was this before? This was, we said, this formula, f of x plus h over minus f of x over h, we said that was the slope of the secant line. So if now we say what happens as we approach 0, it's becoming the tangent line, then we can say that this entire limit represents the slope of the tangent line. And so we did this last chapter. We kind of had this formula. We saw it a couple times. And so, the way I like to do this problem is start off with f of x plus h. And so we're going to plug in x plus h anywhere we see an x. So negative parentheses x plus h squared minus 4 parentheses x plus h plus 1. It's going to give us negative x squared plus 2xh, right? We're going to FOIL that out, plus h squared, or use the shortcut, minus 4x minus 4h plus 1. And so that's negative x squared minus 2xh minus, right, that negative should be distributing to all three, h squared minus 4xh minus 4h plus 1. So I'll use another color. So the limit as h approaches 0 of, again, all of this is our f of x plus h. So I write it out first, so I'm not having to rewrite the word limit every time and all that other stuff. So this was all of the f of x plus h. Then minus f of x. So when I subtract f of x, I can either put it in parentheses and put this entire thing in parentheses because I'm subtracting all of it, or I can just change the sign of each value, and I like to do that. So minus negative x squared becomes plus x squared, minus negative 4x becomes plus 4x, minus 1 becomes minus 1. And all of that is going to get divided by h. So let's see what cancels out. So negative x squared cancels out with positive x squared. Negative 4x cancels out with positive 4x, and positive 1 cancels out with negative 1. A hint for you guys is really all of the terms on the right side, the f of x terms, generally cancel out. I'm going to write this up here because that's where I have room to do it. So this is the limit as h approaches 0 of negative 2xh minus h squared minus 4h all over h. And you can factor out an h, or you just kind of remember the shortcut, which is if there is an h in every single term, you can cancel it out because it's like you factored it out. So this then ends up being the limit as h approaches 0 of negative 2x minus h minus 4. We're going to plug in 0, and that gives us negative 2x minus 0 minus 4. Okay, so I want to point something out about this. We got this value, negative 2x minus 4, right? But we said already that this was the slope of the tangent line. So what that means is negative 2x minus 4 is actually also the slope of the tangent line now for any x value. So if we went back to Desmos, negative x squared minus 4x plus 1. So I'm going to change our function to negative x squared minus 4x minus 1. And I have to zoom. Actually, I'm going to just reset this. Let's do this. I was way zoomed in, so I'm just zooming out so we can actually see our graph. So here's our new graph, and A is just our x value, okay? So for any x value, right, this is the secant line, but if I made a tangent line here, that would be our slope. So it's kind of neat to see. So anyways, coming back to this, what we're going to call this, we're going to name this the derivative. And so we're going to name that negative 2x minus 4, that process, that slope of the tangent line. We're going to name that the derivative. And we write the derivative as f prime of x. So that's not apostrophe, we call it prime. Right, so f prime of x. So we're going to kind of look at what the derivative represents as we come down here. So we've done this already. We said that for, f of x equals negative x squared plus 4x plus 1, right? That's the same equation we had. We said that the value of the derivative, right, f prime of x was negative 2x minus 4, right? That was from doing this process. So let's just plug in, so for negative 4, f prime of negative 4 would be negative 2 times negative 4 minus 4. That's 8 minus 4, which is 4. So now what we can do is at negative 4, right, if we drew a tangent line, right, the slope would be 4, like up 4, up 1, 2, 3, 4, over 1. We could kind of imagine the tangent line, down 1, 2, 3, 4, over 1. The tangent line would be going through those points, okay? And if, we do this again for negative 2, right? So f prime of negative 2 is negative 2 times negative 2 minus 4. That's 4 minus 4, which is 0. So at negative 2, our slope is 0, which kind of makes sense because if I tried to draw a tangent line here, it doesn't have a slope, it's just horizontal. So we call that a horizontal tangent line. And then our next one we will do for negative 1. So f prime of negative 1, we plug that in. Negative 2 times negative 1 is positive 2. Positive 2 minus 4 gives us negative 2. So here our slope of our tangent line would be down 2 over 1, down 2 over 1, right up to left 1. So we could draw that line, and that's the tangent line at negative 1. And so kind of visually when we look at this, what happens is that f prime of x, right, is an equation that we can kind of use to draw that tangent line. And what's going to happen, what we're going to see later on is kind of how that connects to f of x. So we'll get there. So our definition of the derivative, we're going to say is that it's f prime of x is equal to f of x, I forget the limit. Don't forget the limit. The limit as h approaches 0 of f of x plus h minus f of x all divided by h. And we can add on to this that f prime of a, if we plug in an a value, that's what we were doing over here, right? This would be like f prime of negative 4. That would be for like a equals negative 4, right? And we got the answer of 4. So what did that represent? That represented the slope of the tangent line. So f prime of a represents the slope of the tangent line to the graph of f of x at x equals a. So that's our definition. So let's find the equation of the tangent line for a few of these guys. So if we want to find the equation of the tangent line at x equals negative 4, right, we know that the slope is negative 4. And we know that the tangent, the point, right, like if we look at the point here on the graph, the original graph, right, we could have plugged in negative 4 to f of x, but I'm just going to use the graph. So the value here is negative 4 comma 1, right? So we know that we have a point at negative 4 comma 1. That's like our point. So we can use point slope form, right? Y minus y1 equals m times x minus x1. And again, to get this point, I looked at the graph to find the y value, but I also could have plugged in negative 4 into the original. So this gives us y minus 1 equals negative 4 times x plus 4. So that's our value of our equation. That's this first equation. I probably should have done this in the color black to match up with it, but that was that first equation. Okay, now can I distribute it? Absolutely. negative 4x minus 16, add 1, y equals, this should have been, did I mess that up? I messed that up. This was positive 4. Okay, so the slope was positive 4, so this was positive 4, that's positive 4, so this is positive 16. So then we get y equals 4x plus 17, right? This would be in slope form, slope-intercept form. But I don't really care which way you do it. I always leave my answers in point-slope form. But on the AP exam, sometimes if it's multiple choice, they might solve for the y. So just be okay doing that. So let's go ahead and look at the second one. So the slope at negative 2 was 0, right? And then our point up here, if we did this as a point, our point is 2, 5. So we have the point 2, 5. So we can say y minus 5 equals 0 times x minus 2. And this is probably the one that I do solve. This technically is correct, but I usually solve this one because of the 0. 0 times anything is 0. So this is y equals 5, right, which is just a horizontal line, which makes sense because it was a horizontal line. And then our last one, I'm going to do this in blue because that's what it is. Our slope is negative 2 for the equation at x equals negative 1. And then the point we have is at negative 1, 4. So that's the point there. And again, you could have plugged in negative 1 to the equation, right, to this original equation, not the derivative one, but this original equation. If you plugged in negative 1 for the x's, you'll get the answer of 4. But since we have it graphed already, I'm going to use the graph. It's easier. So y minus 4 equals negative 2 times x plus 1. And I'm going to just leave this one like this. I'm not going to worry about solving it. So those are the equations of those tangent lines. So whenever we hear the word derivative, we want to think slope of the tangent line. And whenever we hear slope of the tangent line, we want to think derivative. And so now that we're kind of understanding that, we're going to just do these analytically and just practice a couple of them. So we're going to just kind of practice using this formula for a couple different equations. So if we had f of x equals 2/3 x, again, what I always like to do first is just plug in, and then I actually do the limit. So 2/3 x plus 2/3 h plus 3. So now I'll do my limit. So the limit as h approaches 0 of 2/3 x plus 2/3 h plus 3, and then minus f of x. F of x is the original. So I flip both sides, minus 2/3 x minus 3, all over h. And I told you if you did it correctly, these should cancel, and the negative 3 should cancel, which they do. So we get the limit as h approaches 0 of 2/3 h all over h. Our h's cancel out. So we have the limit as h approaches 0 of 2/3. There's nothing to plug in, right? You don't plug it in anywhere, so it's just 2/3. So what this kind of tells us is that for y equals 2/3 x plus 3, the tangent line always has a slope of 2/3. And that actually makes sense because if we think about this original equation, 2/3 x plus 3, 1, 2, 3, it's a line up to over 3. And so it's always a line. So the tangent line would be the same. So the tangent line would always have a slope of 2/3 because it's not really a curve, it's just a straight line. So that's why there's no x value. Okay, next one, f of x plus h would be 1/2 x plus h squared minus 2 x plus h plus 3. That gives us 1/2 x squared plus 2xh plus h squared. You should memorize the shortcut. It makes life so much easier. So again, the shortcut for kind of foiling out, if I had x plus 3 squared, is I square the first term, I multiply them, and then multiply by 2. So 3x times 2 is 6x. And then I square the last term. 3 squared is 9. Okay, so we'll distribute this. 1/2 x squared plus xh, right, the 2's cancel, plus 1/2 h squared minus 2x minus 2h plus 3. So now we will plug this into our limit. And we're just going to rewrite all of that. This is kind of tedious, but it's important that we show all of our work. So minus 1/2 x squared, change the sign, plus 2x, and then minus 3, because we're subtracting 1/2 x squared. We're subtracting negative 2x, turns it positive, subtracting negative 3. All of this divided by h. So again, if we did this correctly, the negative 1/2 x squared should cancel, it does. 2x should cancel, it does. Negative 3 should cancel, it does. So this gives us the limit as h approaches 0 of xh plus 1/2 h squared. As I'm writing this, a reminder that we always write limit if we still have, now in this case I said x's earlier, but we're using h. So if we have h's in this case, we're going to still write the limit. So as long as we have the h's there, we're going to write the limit. So now here, I have an h everywhere. So I can cancel out an h everywhere. This should have been 1/2 h squared. So those h's cancel out, and I get the limit as h approaches 0 of x plus 1/2 h minus 2. We're going to plug in h for 0, and that gives us x minus 2. So what this means is the derivative of f of x is x minus 2. And really, we could write this as f prime of x equals x minus 2. That's probably a better way to write this. So I'm going to go back here and write f prime of x equals 2/3. Let's write it that way. So I kind of already talked about this, noticing that, okay, this one, 2/3 didn't have an x, this one does have an x. And the reason for that is, if we kind of think of the graphs, right, 2/3 x, we already graphed it, but we said it's up 3, and then up to over 3 for our slope. And then 1/2 x squared minus 2x plus 3 is going to be a parabola. Honestly, I don't know exactly what it is, but I'm just going to draw a parabola. But essentially, right, if I wanted to draw a tangent line here, it's going to be different than a tangent line here. So the derivative should be changing. The slopes of all of these are different, right? Because remember, the derivative represents slope. So since there's an x in it, that means that it's a variable, it's changing. So the slope is changing, which makes sense on the graph, it is changing. Whereas with the 2/3, right, the derivative of the line was just 2/3. There's no x, so it's a constant slope, which makes sense. You might have heard your teacher in Math 1 say, like, constant rate of change, right? For a line, it does have a constant rate of change. But on the parabola, it did not have a constant rate of change. It was changing. So we'll do a couple more examples of these, and then kind of wrap it all up. So the limit, before we get to the limit, actually, we're going to do the f of x plus h. So f of x plus h would be the square root of x plus h plus 2, and that's it, right? We just, wherever x is, we put in x plus h. So this one's going to be the limit as h approaches 0 of the square root of x plus h plus 2 minus the square root of x plus 2 all over h. Okay, and this one again, I'm not going to really test you on this, but this would be where we would have to do the conjugate. Square root of x plus h plus 2 plus square root of x plus 2 over multiplied by the square root of x plus h plus 2 plus the square root of x plus 2. So we're just kind of changing that minus to a plus. And the reason we do that is when we FOIL it out, the middle terms are going to cancel out. So I always skip that step. I've shown it before. You can FOIL it out fully if you want to, but when I do the square root of x plus h times itself, the square root just cancels out. So I get x plus h plus 2. Then I'm going to have these multiplying, but I'm adding that and multiplying, subtracting it. Those middle two terms, when I do the FOIL, are going to cancel out. So I skip them. And then minus x plus 2 times x plus 2 cancels out. But be very careful, put that in parentheses, because the negative is going to distribute. So this is the limit as h approaches 0 of x plus h plus 2 minus x minus 2 all over h. 2's cancel, x's cancel, and we get the limit. This is my fault. This in the denominator had square root of x plus h plus 2 plus square root of x plus 2. Right? We need to multiply that. Square root of x plus h plus 2 plus square root of x plus 2. So don't forget about your denominator. So in the numerator we have h, and in the denominator we have h times the square root of x plus h plus 2. Now we could have distributed this, but just like I told you guys last chapter, whenever we're doing these conjugates, you want to kind of expand FOIL out this side that had the conjugate, and then the other side we're just going to go ahead and leave it factored. So we're going to leave it, kind of factored and multiplied. We're not going to actually factor it out. And the reason we do that is that 99% of the time, something's going to cancel out. So this now gives us the limit as h approaches 0 of 1 over the square root of x plus h plus 2 plus the square root of x plus 2. And so we're going to go ahead and plug in 0 to our h. I'm going to write this off on the side. So when we do that, we get 1 over the square root of x plus 0 plus 2 plus, again, x plus the square root of x plus 2. So just like how x plus x is 2x, the square root of x plus the square root of x is 2 square roots of x. So in this case, this is going to be 1 over 2 square roots of x plus 2. And so I'm going to write that as the derivative. F prime of x equals 1 over 2 square roots of x plus 2. And so, kind of showing this one more way that this could happen. Again, this is a trickier way, is with a rational expression. So f of x plus h, again, is going to be easy, but then the limit part's going to be harder. So we plug in x plus h, we get x plus h plus 2. So we can jump straight to the limit. So 3 over x plus h plus 2, and then minus 3 over x plus 2, all divided by h. So we want to, combine like denominators so that we can add the fractions. So I'm going to multiply this side by x plus h plus 2, x plus h plus 2, and then multiply the left side by x plus 2 and x plus 2. Same thing as before, we're going to expand out the numerators, but we are going to leave the denominators factored. So in the numerators, we're going to multiply the 3, expand it, so 3x plus 6. And then in the denominators, we're going to go ahead and leave those factored. X plus 2 times x plus h plus 2 minus, we're going to go ahead and expand that. So 3x plus 3h plus 6 all over factored x plus 2 times x plus h plus 2. And the big mistake I see here is do not forget it's all over h. Okay. So now the limit as h approaches 0, now we can add the numerators. So 3x, don't forget the minus, right? This is going to be, minus 3x minus 3h minus 6. So 3x minus 3x, those cancel. Negative 6, positive 6 cancel. So this is going to be negative 3h over x plus 2 times x plus h plus 2 all over h. And there are a lot of ways you can do this. You can lollipop the h and multiply by the reciprocal. Some of you guys might just kind of realize that the h's can just straight cancel, which is kind of a hard thing to do, but it happens when a term is, if you have two fractions like that, when it's in the numerator and the numerator, or the denominator and the denominator. Or the way I prefer to do this is just get rid of my fraction by multiplying by the denominator of the fraction to both sides. So that cancels out. And so then we get the limit as h approaches 0 of negative 3h over h times parentheses x plus 2 times parentheses x plus h plus 2. And now our h's will cancel out. And so now we have the limit as h approaches 0 of negative 3 over x plus 2 times x plus h plus 2. And our last step will be to plug in 0 for the h. This gives us negative 3 over x plus 2 times x plus 2. And whenever you have something repeated, I'm going to write this right here. I'm going to write this as squared. So that's negative 3 over x plus 8, not x plus h, x plus 2 squared. So that's our derivative. Okay. I know these are very long. This is turning into a long video. I'm sorry. Hopefully most of the videos I'm going to try to keep to like 20 to 30 minutes. But you're not going to have homework, so it's worth it if we have a couple longer videos every now and then. So this next one says to find the equation of the tangent line. So at x equals 7. So whenever I'm finding an equation of a tangent line, we're going to do this a lot in calculus. What I really like to do is I like to write x1, y1, and m. And the reason I do this is because our formula is going to be y minus y1 equals m times x minus x1. So those are the three things that we need, our x1, y1, and m. So we have x1 at 7. To get y1, you just plug it into the original. You always plug it into the original. So to get y1, we just do the square root of 7 plus 2. That's the square root of 9, so we get 3. Now, technically you're going to get 3 and negative 3, but because this is kind of the positive square root side, we're just going to use 3 for this one. And then to get the slope, to get the m, that's where we have to go and do that, that derivative, okay? But I'm not going to make us redo it because I chose these on purpose because this is the same equation. So we already figured out that f prime of x up here was 1 over 2 squared of x plus 2. And so remember, we called m the slope of the tangent line. So for m, we just plug in 7. So to get our m, we're just going to plug in f prime of 7. So 1 over 2 square root of 7 plus 2. It's going to be 1 over 2 times square root of minus 3, which is 1 over 6. So our slope is 1 over 6. So this is going to then give us y minus 3 equals 1/6 times x minus 7. And that is our equation, right? You could solve for, you could go ahead and solve for y if you wanted to. But I'm going to go ahead and just going to leave this here. And I like that answer. So same thing over here, same process. Like I said, anytime a question ever asks me to find the equation for the tangent line, my process is always to write x1, y1, and m. So x1 is 1. To get y1, I plug in 1 to x. So the y1 would be 3 over 1 plus 2. That's 3 over 3 is 1 again. And to get m is going to be f prime of 1, which this is 3 over x plus 2. That's the same equation that we just solved for, 3 over x plus 2. So our slope was right here. So that's negative 3 over 1 plus 2 squared, right? Instead of x, I'm plugging in 1. So that's negative 3 over 3 squared. That's negative 3 over 9, which is negative 1/3. So for our tangent line, we just plug it into our formula. Y minus y1 equals m times x minus x1. And there's our equation. So I'm going to go ahead and skip this because we're not quite set on our graphing calculators. But if you want to try this, this is something you could try if your calculator's working. What you would do is that you would basically plug in the original, so y equals square root of x plus 2 on your graphing calculator. And then you would plug in the tangent line. So you would solve this for y. I'm going to kind of help you out. If you solve for y, if you isolate y, you get 1/6 x plus 11 over 6. And then you would kind of verify that it was a tangent line. You can use it on Desmos too, but if you want to try it on your graphing calculator and get a little experience there, it would be kind of cool. So I just want to kind of recap this lesson. So what we did first was, this is the first example. I'm not going to scroll back up, but this was the first example. We got a derivative, and our derivative was called f prime of x, and we solved it, and it was negative 2x minus 4. Then for f prime of x, we did f prime at negative 1, and we plugged it in, and we got negative 2. Right? So it was negative 2 times 1. Negative 1 was positive 2 minus 4 was negative 2. And so I want to kind of show another formula to get that same answer of negative 2. And so this formula looks a little bit different. But if you notice, there's not h approaching 0 at the bottom, there's x approaching a. So this is the formula, not for f prime of x, but for f prime of a. So what we would say here is another way to do this would be to do f prime of negative 1 equals f of x minus f of 1 over x minus 1. And don't forget the limit. Again, I forgot the limit. So the limit as x approaches negative 1. Now for f of x, we're going to just use the equation. Negative x squared minus 4x plus 1 minus f of 1, negative 1, all over x minus negative 1. So we, if we did this, that's going to be the limit as x approaches negative 1 of negative x squared minus 4x plus 1. Now for f of negative 1, we would have to plug in f of negative 1 to the original. So that's negative 1 squared minus 4 times negative 1 plus 1. That's negative 1 plus 4 plus 1. So that's 4. Okay, be very careful about this negative symbol, right? I talked about that in a previous lesson. This goes outside of your parentheses when you plug in. So this will be minus for f of negative 1 minus 4. And this is going to become x plus 1. So we can write this as the limit as x approaches negative 1 of negative x squared minus 4x minus 3 all over x plus 1. And don't worry about factoring. You don't have to factor. You just plug in negative 1. Right? The first step with limits is always to just plug in the value. So when we plug in that value, we get negative, and then parentheses, negative 1 squared minus 4 times negative 1 plus 3, minus 3. All divided by negative 1 plus 1. Okay? And so we do get 0 over 0, which is kind of frustrating. But when you get 0 over 0, what do? You factor out. So let's see if we can factor out. So the first thing I'm going to factor out is I'm going to factor out the negative symbol. It just makes our life so much easier. So whenever I have a negative with an x squared, I just factor out a negative symbol. What that does is that switches all of the signs inside the factored part. And so now this is going to equal the limit as x approaches negative 1 of negative x plus 3 and x plus 1 all over x plus 1. And what you're actually going to see is this formula you always have to factor. So you can kind of memorize that. You don't actually have to plug in ever. You can always know that you're going to factor. So this gives us the limit as x approaches negative 1 of negative x plus 3. Plug in negative 1. That's we're going to drop the limit because we plugged in. All right, so negative 1 plus 3, and that gives us negative 2. So this is the same answer. Now, it's up to you what you think is more work or less work. Honestly, a lot of times, actually, what I did in blue is less work, because if you remember, what we had to do in order to get that negative 2, right, this was the negative 2, but what we had to do first we had to do the regular derivative. So first we did the derivative, we found out that it was negative 2x minus 4, and then we plugged in negative 1 into negative 2x minus 4. So an alternative formula for that derivative at negative 1 is the limit as x approaches a of f of x minus f of a all over x minus a. So kind of showing it one more time, you could do it with the square root of x plus 2. I'm not going to finish this one, but what we did is we found that f prime of x equals 1 over 2 square root of x plus 2. And then when we did our derivative, right, our derivative at 7 was 1 over 2 square root of 7 plus 2, which gave us 1/6. So we did that work, right? So another way to do this would have been to say, hey, let's do the limit as x approaches 7 of f of x minus f of 7 all over x minus 7. And so what that'll give us is the limit as x approaches 7 of square root of x plus 2 minus, now if you plug in f of 7, square root of 7 plus 2 is square root of 9, so that's minus 3 over x minus 7. Okay, and again, I'm not going to finish this one just because this video is way too long, but what you would do is multiply by square root of x plus 2 plus 3, multiply by square root of x plus 2 plus 3, and you'll end up with getting the x minus 7's canceling out, and eventually you'll end up with 1/6. So what we're saying is that this limit represents the slope of the tangent line at x equals a specifically. So like specifically at x equals a. So that's as opposed to our other formula, which this formula, right, was the slope of the tangent line basically at any x, like in terms of x, right? So it's kind of more of a general formula, whereas our other one, our new one, is a specific formula. So we're going to use both, but kind of looking at this, if we complete this table, you could pause the video and try to do it on your own, but I literally just gave both the answers. So this first definition of the derivative, so this is basically represents the derivative f prime of x the slope of the tangent line to f of x at any x. So it's kind of like our general formula. Okay. And then this alternative form with the x approaching a, that represents the derivative, or we're going to say, why don't we say the value, right, because we're going to plug it in. So we're going to get a number of the derivative, right, which we're saying is the slope of the tangent line, at a point x equals a. So this is our specific derivative. Okay. So I know this was probably one of the longest videos we're going to do all year. I'm sorry, I know how long it was. But the nice thing is, this homework we're going to complete on Monday. And so hopefully, you won't have any homework on Monday other than watching the next video. So you're going to submit the PDF notes of this to the Google Classroom by Monday at 11:59. I don't care if you do it, tonight, tomorrow, but by Monday, 11:59, you're going to submit a PDF of these notes. And then the first few minutes of class, we'll go over any questions that you guys had.